So the first one, so it is the it is an integral that involves that involves an integrand that involves some periodic functions, and the domain of integration, like the range of the integration, is finite. So it is going from 0 to 2 pi, and the functions in the integrand are periodic functions. So you see the cos theta has a period of 2 pi and cos 2 theta has a period of pi. So these kinds of problems are easier. So to do this, first we substitute z equal to e to the power I theta, and where theta runs from, so theta runs from 0 to 2 pi here, and when we substitute z equal to e to the power I theta, that means of course that means mod z equal to 1. So this is actually the unit circle centered at the origin. So our complex variable z lies on the unit circle centered at the origin. Okay, and since theta runs from 0 to 2 pi, we trace the unit circle once and completely. So okay, so if we substitute z equal to e to the power I theta, that means d theta is dz by ij, and mod z equal to 1. And as we all know, cos n theta means e to the power I n theta plus e to the power minus I n theta divided by 2. And if we substitute z here, so we will get this half z to the power n plus 1 by z to the power n. So that is all the substitutions that we have to do. And as I said, sorry, there is a typo. Since theta goes from 0 to 2 pi, we actually trace this unit circle a full revolution, and most importantly in the counterclockwise direction. So as we know, the convention is whenever we go in the counterclockwise direction, theta increases. So in the counterclockwise direction, theta increases from 0 to 2 pi. And then we will so now we will substitute all these things into this integrand. So most importantly we will substitute cos 2 theta. Let's see what happens. So now I have just substituted. So cos 2 theta is half z squared plus 1 by z squared, and d theta was dz by ij, and then 5 minus 4 cos theta. So 5 minus 4, 2 cos theta means z plus 1 by ij, and that is why I have written here 2. Now simply, so I have rationalized the numerator and denominator, like I have expressed the numerator and denominators both as polynomials. So you can easily see that is the case. So please follow this pointer. So step by step I will guide you. So from this first line we can easily get to the second one. Now we will like to factorize in the denominator. So it can be easily done, and this is the factorization of the denominator. So z minus 2 and 1 minus 2z. Okay. So now our denominator has 3 factors: z square, z minus 2 and 1 minus 2z. Now to evaluate the complex contour integral, so what do? We look for zeros of the integrand. Okay, zeros of the integrand. So since this is already expressed as a rational function, and our numerator is an entire function, so of course z to the power 4 plus 1 is an entire function. It is nowhere singular. So the singularity of the integrand will only can only come from the zeros of the denominator. So let us now look at the zero of the denominator. So since I have already factorized it, so you can easily find the zeros. So z equal to 0 is one of the zeros, z equal to 2 is one, and z equal to half is another one. So the denominator has 3 zeros. Okay, and as I have said in the second session, so to evaluate the complex contour integrals, we must always express in these form, like 1 minus 2z must be expressed in z minus half and multiplied by minus 2 in this form. So like so what do we have in the Cauchy integral formula? It says the integrand is fz divided by z minus a. Okay, so z minus a. So in the denominator, z is on the left side always. So in all the factors, z must be on the left hand side, and you have to bring out appropriate factors of minus 1 or some constant factors to express the denominator in that form. So that is what I have done here with 1 minus 2z. I have extracted a factor of minus 2, and that gives me z minus half, and the minus 2 factor that I had extracted, so I have multiplied this in front, and that gives me 1 minus 4i, because 1 minus 2i multiplied by 1 by a minus 2. So this is the integrand, and now of course, so you see z equal to 0 is a second order pole, z equal to 2 is a first order pole, and z equal to half is another first order pole. And now we have to find out which ones of these singularities lie inside the contour. Okay, that is what we do, and our contour is mod z equal to 1, so the unit circle. So of course we can immediately recognize that the singularity at z equal to 2 will lie outside this circle, and only the singularities at z equal to 0 and z equal to half lie inside this circle. So only these two singularities will contribute to this integral. So that is what I have done. So z equal to half is a first order pole, and there is this 2 pi I factor plus 2 pi I, because we are tracing this contour in a positive sense. And okay, now z equal to half is a simple pole, so that is how it is done, and z equal to 0 is a second order pole, so we have to use the higher order Cauchy integral formula. So this will involve a single derivative because it's a second order pole. So a single derivative of this part, and finally after evaluating the derivative we have to put z equal to 0. And now if you do all these things and add and subtract these contributions, you will get pi by 6 as a final answer. So yeah, so that is that. So this kind of problems are pretty straightforward. So all we have to do is to substitute z equal to e to the power I theta, and in these kinds of problems there is no subtlety with the contour, because the contour is always chosen as mod z equal to 1. So we always get the unit circle centered at the origin as the contour in these kinds of problems. So these kinds of problems are pretty straightforward. So now we'll move on to the actual challenge. The real integrals with the range of the integration variable running from minus infinity to plus infinity, or 0 to infinity, something like that. So most importantly, that range will be infinite. So I think there is no question in this problem. Now let's move on. Yes. So first, the easiest one. So we have to find the value of this real integral. Okay. This is a rational function, and most importantly, the integration variable runs from minus infinity to plus infinity. Okay. See, and from the, if we use the concept of convergence of real integrals from real analysis, we will see that the integrand is nowhere divergent, right? Because the numerator is, of course, it's a differential function, and the denominator is also everywhere continuous and differentiable, and most importantly, the denominator is never zero. Okay, as a function of real variable, the denominator is never zero. So that is why this integrand of the real integral never diverges, and this real integral is convergent and well defined. So we will see in the final problem that that is not always the case, and when the real integral is actually divergent, we have to introduce the concept of Cauchy principal value. Okay, but in this problem, since the integrand is well defined everywhere, so we don't need to think about that. So what do we do? Okay. So to evaluate this integral, so let us consider this complex contour integral. So this one. So you will think that I have written x just as z, but most importantly, this is the contour. So we will be doing this complex contour integral over a closed contour. Okay, and the contour that we will consider is depicted here. So here, let us look at this contour carefully. So this is real z, means this is the x-axis. Imaginary z means this is the y-axis, and this is our contour. Okay. Actually our real integral lies along this real line. As you see, our real integral was minus infinity to plus infinity. So along this real line, it goes from minus infinity to plus infinity. So this much was the real integral, but now we are also considering the contributions from this arc, from this semicircular arc. So that is what we have to figure out, how much it contributes. And we do this closed complex contour integral to use the Cauchy integral formulas. You see, we will just simply pick out the contributions from poles that lie inside the closed contour, and that makes our life a lot easier. Doing these kinds of real integral using only real analysis techniques is very time consuming. Okay, so here I will discuss about this contour. So as I said, Cx goes from minus infinity to plus infinity along the real axis. As you can see, this is the this is the part of the contour that lies along the real line, Cx. Okay, and this Cr infinity, so that is the semicircular arc. So it is a semicircle of radius r going to infinity, and this semicircle is centered at the origin. So that means this semicircle lies on the upper half plane. Okay, so it doesn't extend to the lower half plane. So these are the two parts of our contour. Okay, thus the counterclockwise contour C encloses the whole upper half plane C. The union of these two contours thus encloses the whole upper half plane, because we have taken r to the radius of the semicircular arc as infinite. So, and most importantly, you see, there is a sense of continuity in the direction of this closed contour, right? So, since our real integral was from minus infinity to plus infinity, I have put the arrow in the cx part like this. So, this arrow denotes so minus infinity to plus infinity, and to make the closed contour continuous. So of course, uh, with a little common sense, so this arrow should extend from this real line to this contour like this. So this will extend in the semicircular arc in the counterclockwise direction. So that is why I have drawn this arrow like this, and again. So and then again getting into the real line, this goes into this cx direction. So that is how we denote the arrows, and that is how we determine the sense in which the contour, the closed contour is traced. So here the contour is traced in the counterclockwise sense. So that is what I have written. Okay. So now let us note that on Cx, as we know, Cx was the real line. So on Cx, so here as we all know, z is x plus iy. So on the real line, y is 0. So that is why on the Cx part, z is x only, and that means dz is dx. And how do we parameterize the infinite radius semicircle? So this semicircular arc, so on this we parameterize z as z equal to r e to the power I theta. And since we trace this in the counterclockwise direction, then theta goes from 0 to pi c, and dz is I r e to the power I theta d theta. So just like the problem we considered before. So if we take mod z here, so mod z will be r. So that, and since theta goes from 0 to pi, so we only trace the infinite radius circle up to only the half of the circumference. So that is why it's a semicircle. So I hope these two parameterization of these two parts of the contour is clear. So now we will just substitute these two parameterizations. So our complex contour integral was this one, the left hand side, and now I have separated out the contributions from each of these two parts. So I have written them separately. So one is along this Cx and one is along this CR infinity, and most importantly these two integrals are not along a closed contour. So that is why even though the left hand side is a closed contour, the contours in the right hand side are not closed one. See, as we have seen, so Cx by itself was not closed, and CR infinite, which is a semicircle, of course it is not closed, but when those two are combined together, we get a closed contour C. Okay, so that is why in the right hand side I have not put this contour integral sign, the closed contour integral sign, but only the contour integration along these two open contours. Okay, now I will substitute. So for Cx, I have just substituted z equal to x as we discussed, and for this semicircular arc, I have substituted z equal to r e to the power I theta. So this is plain and simple substitution. Now we will infer the contribution from these two parts. Like first let's look at the semicircular arc. So you see, if let us consider the modulus of this second term. Okay, so this is the modulus, and of course we know that this modulus, so yeah, there is a theorem, so that is the extension of the triangle inequality. So this says that the modulus of a complex integral must be less than or equal to the integration of the modulus of that function. So this is modulus of integration, and this is integration of modulus, and this one must be less than or equal to this one. So this you can think as the Cauchy-Schwarz inequality or the extension of the triangle inequality. Simple. I hope this was discussed in the lecture, right? Should be. Okay. This is an important concept. So okay. So now we will look at this integration of the modulus. Okay. And now what will be the modulus of this function? So here I have written simply the modulus. So it's nothing difficult, but only keeping track of all the terms. I have got this one. So this is the modulus, and we have to do the integration of this modulus, and this is real integral. So d theta, and d theta goes from 0 to pi. And most importantly, r is infinity. Okay, but as you see that we will not need to do this integration, because in this r going to infinity limit, what is this integral? So in the numerator we have r to the power 4, in the denominator we have two factors, and both factors are polynomial of degree 4, right? So numerator is the polynomial of degree 4, and the denominator have two factors, both of which are of degree 4. So that means our denominator is a polynomial of degree 16. Of 16? No, I don't think so. Of 8. Okay. Yeah. So the denominator is a polynomial of degree 8. So r to the power 4 multiplied by r to the power 4 gives us r to the power 8. And when we take r going to infinity limit, that means this is 0. This integrand is 0. So this is simple real calculus, real variable calculus. So easily this integrand in the r going to infinity limit gives us 0. So that means we don't have to do this integrand, and we can simply write the result of this integration, which is 0. Okay, I hope this limit is clear. If not, please let me know. Okay, move on. So what do we have? So we have the modulus. Oh, sorry, we have the integration of this modulus is 0, right? And what did we say? We said that this integration of modulus must be greater than or equal to the modulus of the integration. So the modulus of the integration must be less than or equal to 0. But we know that the modulus is 0 or greater than 0, right? So here we are left with the only option, which is the modulus of integration is 0. So this is the only option that we have here. And as we all know, if a complex number has modulus 0, it is itself 0. So that means this integrand, so this integrand here, the second term, so this term is itself 0, because its modulus is 0, as we have seen. So this term is 0. Now we are left with this. So we are left with, okay, so this second term is 0, and we are left with this complex contour integral over this closed closed contour is equal to the real integral that was given in the question. So now we are left with this. So this was given in question, and this is what we deduced to be equal to. So this is the complex contour integral that we just showed. This real integral is equal to. And now we will evaluate this complex contour integral. And this is easy to do. We have dealt with much more difficult integrals. Okay, and you see, so this integrand again, our contour is the, okay, we will discuss later, but how do we find the points of singularities of this integrand? So we see the numerator is an entire function, but denominators are two second degree polynomials. That means the denominator will have 4 zeros, right? And the 4 zeros, so I have not mentioned them explicitly, but I have directly written them on this contour. So these bold dots, so these are the points of singularities of our integrand. So this is the integrand. So you see, so z square plus 1, so this is 0 when we have z equal to plus sign and z equal to minus sign. And this z square plus 2z plus 2, this is 0 when z is minus 1 plus I and z is minus 1 minus I. So these are the 4 points of singularities of that integrand. And now we have to figure out which one of these singularities will lie inside our chosen contour, right? And we see, since our chosen contour encloses the whole of the upper half plane, so only those points of singularities that lie on the upper half plane will contribute to this contour integral. So what do we have? So we have this plus I and this minus 1 plus I lying on the upper half plane, and the other two contours lie on the lower half plane. So that is why these two contours that are on the lower half plane will not contribute to the integral, because our contour does not enclose them. So that is why I have written here. And you see, so all of those four points of singularities were simple poles, right? So now we will simply use the Cauchy integral formula here, and we have simple poles. So do this. There is this 2 pi I factor, and just substitute z equal to I in this function and z equal to minus 1 plus I in this function, and do all this, substitute these values and do the simplification, and you will get minus pi by 5. So that is our answer. Here I have written. So z equal to I and z equal to minus 1 plus I are only two simple poles that contribute to this contour integral. So yeah, that is how we solve this problem. Okay, if you don't have questions, so then I will move on to the next problem. So again, we have to compute a complex integral, compute a real integral where the range of integration is again infinite. So but now be careful, it runs from 0 to infinity. Earlier it was from minus infinity to plus infinity. And there we have this specification. So a is greater than 0 and m is greater than 0. So we'll see this specification will be important. So here, let us do this real integral, and we see the integrand of this real integral is an even function, right? Cos ax is an even function, and so is x square plus n square. So the integrand is a real function. So we can convert this 0 to infinity integral into a minus infinity to plus infinity integral like this. So there is a factor of half, extra factor of half, and this gives us minus infinity to infinity. This is just the usual real integral formula. So this one, and we see, and since this is a real integral, of course the value of this integration will be a real value, and then okay, and cos ax is the real part of e to the power I ax. Okay, so that is what I have written here. So we'll finally, the answer will be the real part of this integral. So e to the power I ax is here. So of course, as you might have guessed by now, so the complex integral that we will take will be this. So this is the complex integrand e to the power I a z divided by z square plus n square whole square. This is our complex integrand. And let us now look at this contour. What will be our closed contour? So this is our closed contour. Again, much similar to the previous one. So a real line Cx, and then this semicircle of this infinite arc, and again the direction of the contour is this one, and this is fixed by this minus. We are going from minus infinity to infinity. That is why we are going in this counterclockwise direction, just like in the problem we discussed before. Okay, so this is the contour. Again, the contour is two parts. One is Cx and one is the semicircular arc. And now we will separate out the contributions from these two parts like we did before. So here I have separated out. This is for Cx and this is for the semicircular part. And we all know that on this Cx, z is simply x. So that is what I have substituted in this part. And in the second part, I have substituted z equal to r e to the power I theta, where theta goes from 0 to pi. Here, please compare with the previous one. Okay, and this is simple substitution. Now, again, let us first look at this this term. So this are going to infinite term. So again, we will look at this. We will look at this modulus of the integration, which we discussed must be less than integration of the modulus. Okay. So integration of the modulus, and here the modulus of this function is this one, as you can easily calculate. So r e to the power minus r is sin theta, and where this thing we have in denominator. Now there is the crucial part. So since a is greater than 0 and sin theta is greater than equal to 0 for 0, so for when theta is between 0 and pi. So sin theta is greater than 0 there. So because of this, a sin theta is greater than 0, you see, and a sin theta, when a sin theta is greater than 0, this limit in r going to infinite limit must be 0, because you see, so you can easily calculate again in this limit in the real variable calculus. So e to the power r multiplied by some e to the power minus r multiplied by some positive factor in the r going to infinite limit is 0, right? And there you have r, and there you have r to the power 4. So much stronger is the divergence of r to the power 4. That makes the denominator also divergent. Denominator is more divergent than this r factor. So that means in the numerator we have 0 in this limit, and the denominator we have infinity. So this so the integrand is of the 0 by infinity form. So of course that means 0 by infinity means 0 in the language of limit. Okay. Since the integrand is 0, we don't have to do the integration and we simply write this limit as 0. Okay. Now again, since the integration of the modulus is 0, that means the modulus of this integration must be less than or equal to 0. But of course, as you know, so the modulus must be greater than or equal to 0. So that means the modulus again is 0 here, and that means the integration is itself 0 in this are going to infinity limit. So that is why this second term does not contribute to the complex contour integral, and we are left with this. So we are left with this. So complex contour integral is equal to the real integral where x runs from minus infinity to infinity. Now we have this complex contour integral, and we will evaluate this using our Cauchy integral formula. So now let us look at this complex contour integral. So now again we have to figure out which points of singularity lie inside or outside the contour. So you see we have so z squared plus m squared. So there are 2 points of singularities, and those are plus mi and minus mi. Okay, and you see, so plus mi must lie inside the contour because it lie on the upper half plane, and minus mi lies on the lower half plane, and that is not enclosed by the contour. So only plus mi will contribute to this complex contour integral. Okay, and since both of these poles are second order poles, you see, because there is the square, so z equal to mi is a second order pole. Okay, so we have to use the higher order Cauchy integral formula, and since this is a second order pole, so we have to do this single derivative, and single derivative of this function e to the power iaz divided by z plus im square. So after doing this derivative, we have to put z equal to mi, and after simplification we will get this. So this is the value of this real integral. But now we have to relate it to the one that was actually given in the question. Okay, so what was that one that was given in the question? So we have just evaluated this integral, right? E to the power ix divided by x squared plus m squared whole square. So we know the value of this integral, and we have to take the real part of half of this value. That will give us the desired result. So let us do that. So multiply this by half and take the real value, and this is already real. So we have to just multiply it by half, and after multiplication by half, we get this result. So yeah, this is our final result. Okay. So this concludes this problem. Now we are left with the final problem that is much more involved to see the contour. Okay, I hope there is no question. And yeah, which contour to choose will be evident by practice only. So there is no straightforward way to say which contour to use. So we have to look at the functions that is given and then proceed. So again we have to calculate this integral. Again this is the real integral, and again x runs from 0 to plus infinity. So again we do the usual trick, and we can do that because you see x sine 2x, this is an even function. X is an odd function, sine 2x is an odd function and their multiplication is an even function, and x squared minus 1 is already an even function. So the integrand is an even function, so that is why we write it like this. So minus infinity to plus infinity, and at the expense of a factor of half. And okay, and again, so we know sine 2x is the imaginary part of e to the power 2ix, right? And that is why we have to so that is why the integral that is given in the question will be equal to the imaginary part of this integral that I have written here. So now we will evaluate this integral. This is our complex contour integral, z e to the power 2iz divided by z square minus 1. So you see, after calculating this integral, we have to take its imaginary part. So now we have to choose the contour C, but now the problem is that so the integrand has a singularity at z equal to plus 1 and z equal to minus 1. You see, and both of them lie on the real line. So that is where the certainty comes from. So we have the singularities exactly on the real line. In the previous two problems, we did not have these problems. There the singularities were only on the upper half plane or lower half plane, but exactly not on the real line. But here they are exactly on the real line. And what do we know? We know that to use the Cauchy integral theorems or Cauchy integral formulas, the points of singularities must not lie on the contour itself, right? They have to lie either inside the contour or outside the contour. But if they lie on the contour itself, then the Cauchy integral theorem breaks down. So that is why we have to be very careful in choosing the contour. Okay. So now let us look at the contour. Okay, so x runs, so x in the real integration should run from minus infinity to infinity. So from that we can guess that we have to take some form of the real line, but we must exclude these 2 points of singularities. See, that is why I have chosen this contour. So again, so this semicircular, so the large semicircular arc is the semicircle of radius infinity. So that means this point, so please follow the pointer. So this point is minus infinity on the real line. So from the minus infinity on the real line, we have to go up to the left of the point minus 1 along the real line. So that is one part of the contour. Then we have to exclude the point minus 1, and we do that by considering a contour, by considering a semicircle like this. So this is the semicircle C minus. So by considering the semicircle, we circumvent this problematic minus 1 point like this one. So we go along this semicircle from the left of this minus 1 point to the right of this minus 1 point. Okay, and then after going to the right of this minus 1 point, we again continue along the real line until we encounter another point of difficulty. So another point of singularity is plus 1, right? And we have to thus exclude this point. So we continue along the real line from the right of minus 1 to the left of plus 1. Okay, and we have to exclude the point plus 1 from the contour. That is why we choose the contour like this one. semicircle, again a semicircle centering around plus 1, and this semicircle takes us from the left of plus 1 to the right of plus 1. So this is the semicircle that I have denoted as C plus. And then after going to the right of the plus 1, then we have no problems, no points of singularity on the real line. So the rest of the real line is fine, in the sense that there is no problems of no points of singularity. So that is why we continue from the right of this point plus 1 up to the point at plus infinity along this real line. So that is why that is why this part of this real line, excluding this minus 1 and plus 1, is denoted as Cx cross. So Cx cross means I have excluded those finite number of points from the real line. So earlier we had Cx as the real line, so Cx as the contour that extended along the real line. Here we have Cx cross. This is the part of the contour that lies almost along the real line, but leaves out the points of singularities. And then the semicircular arc, the usual one. So these are the 4 components of the closed contour C, and again you can convince yourself of the direction of the contour. So this is again counterclockwise, because we have to go from minus infinity to plus infinity. So again, as I have discussed, the complete closed contour C consists of 4 parts. So this C minus part, that is a semicircle of radius P going to radius P, and of course radius have to be a positive. That is why I have written like 0 plus of radius P, and centered around z equal to minus 1, and this semicircle lies on the upper half plane, right? That is what we have drawn here. And then the second semicircle C plus, again radius almost 0, and centered at z equal to plus 1, and lying on the upper half plane. Yeah, that is what we have drawn here. And then Cx cross, as I said, this goes from minus infinity to plus infinity, excluding the points of the singularities. So that is why we have to leave them out, and that gives us this Cx. So Cx cross goes almost across the real axis, barring those 2 points. And then the semicircular arc, that is of radius r going to infinity, and that is centered around origin, and that lie on the upper half plane. So these are the 4 parts. And now we know the parametrization that we will have to take on the part 3 and part 4 of the contour. We have discussed them on those previous 2 problems. Now, what will be the parametrization along those 2 small semicircles? So on this C minus circle, so we see that was centered around z equal to minus 1. So z must be of this form, z equal to minus 1 plus p e to the power I theta. You see, I have just parameterized the circle of the small radius that is centered around minus 1. And here you see theta goes from pi to 0. Why something like that? Yeah, we start from here and go to here. And our convention is to take pi theta to be 0 here, and all the way round here up to pi here. So, and in these two semicircles, we are tracing in the different way. That is why we go from pi to 0. Similarly, here we go from pi to 0. Okay, that is what I have written, pi to 0. And of course, since z is this, dz is I p e to the power I theta d theta. And similarly, on the C plus circle, z is plus 1 plus p to the power I theta, p e to the power I theta. Same thing, just the parameterization of this semicircle with center at z equal to 1, and again all the, and dz is same. Now I will only need to substitute all these parameterizations. So our complete complex contour integral is this, that is the left hand side, and in the right hand side I have written separately contributions from all the parts of the contour. Okay, so let us start from here. Let us start from this part, this part of the real axis. So that means we go from minus infinity to minus 1 minus p. Here we have taken p tends to 0 plus. That means we go from minus infinity to minus 1 minus p. That means up to the left of the point minus 1. And on the real line, z is x, so that is why I have simply written x here in place of z. And then we go along the left semicircle, and we will have to use the parameterization of the semicircle. That is what I have used here. So just substitute the parameterization of z here in terms of p and e to the power I theta. That is what I have done here, simple substitution. And p was the radius, and of course theta goes from pi to 0 because we are tracing in the opposite direction. And then again, so we reach minus 1 plus p, this is the point minus 1 plus p, and we go along the real line up to plus 1 minus p. That is what I have written, minus 1 plus p to 1 minus p. And again, z is x on the real axis, and thus we continue. And this is for the second semicircle. Simple, use the parameterization again. Okay, and then after coming down to the real axis again along this semicircle, we have from plus 1 plus p to infinity, right? So plus 1 plus p from infinity, and then this is the contribution from the infinite radius semicircle. So this is arguing to infinity, but here theta goes from 0 to pi. See, these are all the contributions. These are all the contributions, and then we have to calculate all these terms separately. Now let's look at the left hand side. So our left hand side is the closed contour that is in this picture, but we see the closed contour does not enclose any point of singularities. So we have left out these points of singularities outside, and inside there is no points of singularities. That means by the Cauchy integral theorem, the left hand side must be 0 because inside the contour there is no points of singularity. And okay, that is one thing. And similarly, as in the previous problem, since on the upper of plane sin theta is greater than 0, then again in the limit r going to infinity, this term will be 0. The term that involves the r going to infinity limit will again be 0. as we have considered in the previous two problems. You can convince yourself that this will be the case. Thus, we are left with this one. So 0, left hand side is 0, and then I have collected all the integrations along the real line. So I have just collected these three terms all along all the integrations along the real line. So these are the three terms, and then in this line these are the two terms that involves the integration around the semicircle. Okay, and this integration, so you see, so these are almost, so let us look at this first term. So we know, so minus infinity to minus 1 minus p, and then there is minus 1 plus p. So if p was 0, we could simply wrote, so okay, if p was 0, so we have taken p tends to 0 plus, but if p was 0, so this would have been simply the real integration from minus infinity to plus infinity, right? Because all of these limits would have cancelled each other. So that is the simple property of real integrations. But here we have excluded but here we cannot take p equal to 0 exactly. So we have to consider this only as a limit. So these kinds of real integrations are called principal value integrations. So we have to write this PV. PV means principal value. So this is the definition of principal value, and in the principal value integration, so principal value of this integration, and where the range of integration is minus infinity to plus infinity. So yeah, so this is one thing. So this was the integration along the real axis, and then the semicircular, the integration along the small semicircles, and here I have cancelled some factors of p from the numerators and denominators, as we usually evaluate the real variable limiting problems. So I just cancel out this factor of p and a factor of p from the denominator, and that leaves us with these two terms. So one is this one, and the another one is this one. Now you will see that, oh sorry, there is a typo. There will be limit p tends to 0 plus here also, and thus we see, okay, so if we just blindly substitute p tends to 0 plus here, we see there will run into no problem. So in the p tends to 0 plus limit, this limit is finite. So is this limit. So I have now just substituted p equal to 0 here. So after substituting p equal to 0, you will get this and this from these two terms respectively. And then this is an easy integration. So e to the power I theta and e to the power I theta gets cancelled from numerator and denominator, and you are left with a constant integrand, and then you have to do this d theta from pi to 0. That gives you a factor of minus pi, and after doing this integration you will easily get this term. Just collect all these terms, and then finally we have this principal value of this integral is equal to I pi cos 2, and I pi cos 2 comes from this term. Please. So, and this is what we are asked to calculate. We are actually asked to calculate the principal value, because in the real variable calculus, you see this integration is actually divergent, because if you put x equal to 1, the integrand diverges, and the real integration does not make any sense. does not make any sense. So that is why we can only calculate the principal values, and that is what we have been asked to calculate. So omitting the principal value symbol, we finally get this. So this was our principal value, and then as we related in the first line, so this was our relation. So this is what was given in question, and this we related with this. So we have to find the imaginary value of this integration, and this integration we have already found out to be I pi cos theta, and then this is I pi by 2 cos theta, and we have to take the imaginary part. That means our answer is pi by 2 cos 2. So this is our final answer, pi by 2 cos 2. So yeah, we must remember that this is the value of the integral in the Cauchy principal value sense, since otherwise the real integral is divergent. So, yeah, that concludes the problem.